Hello everyone from sunny London, stress on sunny, not so usual. So our next speaker is Annika Heckel from LMU Munich, and she will tell us more about chromatic number of random graphs. Annika, all yours.
Thank you very much for the introduction and for the invitation to speak at this event. So I always start these talks with a quick reminder of what the chromatic number is, although I think most of you don't need this reminder, but if you do. So we're always coloring, we want to color a graph so that neighboring vertices, such as this one and this one, get different colors. And the question is, how many colors do we need? Now, as for any kind of basic graph parameter that we have, we can ask ourselves, okay, what happens if we choose the underlying graph randomly? So suppose we pick an n-vertex graph and we pick it uniformly at random from the set of all possible graphs on n vertices. And we work out the chromatic number. Okay, so we've got this result. And now we repeat the experiment. So we pick another n-vertex graph uniformly at random. Now, if we know the chromatic number of the first random graph, how well does that predict the chromatic number of the second random graph? So will it have the same chromatic number as the first random graph? Or if not, how different do we expect the chromatic numbers to be? So if we work out the chromatic number of the first random graph, how much does this help us in predicting the chromatic number of the next random graph? So I guess what we're asking is, of course, the chromatic number of a random graph is a random variable, but does this random variable behave basically deterministically, which means with very high probability we get the same results the second time we try, or are the results maybe completely spread out between, I don't know, in principle it can be between 1 and n. Okay, so until recently we didn't actually know a lot about how different the chromatic numbers are likely to be. We had an upper bound, but we didn't really have much of a lower bound. And yeah, so in this talk, we will look at some lower bounds, at least for some n. So I said we pick an n-vertex graph uniformly at random. Now that's perhaps as a distribution quite hard to generate, you'd think, but luckily we have a nice way of generating a uniform n-vertex graph. So we can just look at GN1/2, where we include every edge independently with probability 1/2, and that gives us a uniform n-vertex graph. More generally, of course, we can look at the random graph GMP. And there are a lot of results about the chromatic number of the random graph GMP. And in general, they usually either talk about the value of the chromatic number. So, well, these past results give upper or lower bounds for the chromatic number, which hold with high probability. Or they talk about the second question, that is the focus of this talk, namely, even if we can't pin down the value of the chromatic number exactly, can we say something about how much it varies? So how wide is the distribution of the chromatic number of GMP? Now, very briefly, I want to talk about the value of the chromatic number. Not in general for GMP, because I have limited time, but for our favorite random graph, GN1/2. So there's a well-known result of Bollobás, who worked out the asymptotic value of the chromatic number. So he showed that with high probability, the chromatic number of GN1/2 is given by, well, this is expression here, n over 2 log n. So this was already known to be a lower bound, so that's not so hard. But he proved the matching upper bound. Now, this result was sharpened several times over the years, and it was also generalized to general P. So there's a similar expression for if P depends on n. And for GN1/2, the best result on the value that we have currently is this formula here. Now I'm writing out this formula because it will become important later when we talk about concentration of the chromatic number. So maybe just keep in mind that we have this formula for the chromatic number. So you don't have to remember the formula, but that it exists. We have this function, and we know the chromatic number is given by this function plus this error term with high probability. Okay, so how about concentration? Of course, this formula here is already a weak concentration type result because it specifies an interval of length little o n over log n squared, which contains the chromatic number of gm1/2 with high probability. Okay, so at least this is an upper bound on how much the results of our chromatic numbers of random graphs will differ if we draw uniform and vertex graphs independently. But if we don't have to specify an explicit interval, this can be improved quite a lot. So the concentration type questions, so the starting point for these is always the famous result of Shamir and Spencer from '87, which is a very general result. So they showed that actually for any function, P of n, there is some sequence of intervals of length about root n, which contain the chromatic number with high probability. Now they don't specify the intervals, and it's kind of a feature of the method that you don't get any information on what these intervals are, but you know they exist somewhere and they contain the chromatic number with high probability. So they proved this using martingale concentration. Now in this general form where you can put in any function P of n, this result is optimal. So for some very special cases, so if you let P tend to 1 at the correct rate, well, you can show kind of for silly reasons that the chromatic number in this case is actually spread out over about root n values. But this is kind of not the random graph we typically look at. So if you put in this P, then you have almost all the edges except for a few missing edges. There are order n missing edges, and kind of whenever an edge is missing, then you can kind of color the corresponding vertices in the same color. And yeah, so the number of missing edges varies by root n, and this is why the chromatic number in that case varies by about root n. But this is kind of kind of a pathological case. So of course, in general, you can ask yourself, okay, can we do something better for the graphs, for the random graphs we actually care about? So first of all, how about the case P equals 1/2? Now here, this result was improved slightly by a log factor. But if P tends to 0 quickly enough, you can improve this quite a lot. So so if P is n to the minus c, where c is a constant, I think you can improve this to about n to the 1/2 minus c. And in particular, if P is less than n to the minus 1/2 minus epsilon, you can reduce the interval length to only 2 values. So this is kind of as sharp as this kind of result can get. So this was proved by Alon and Krivilevich in '97. So they showed if P tends to 0 more quickly than n to the minus 1/2, then in fact here the chromatic number does behave like a deterministic function more or less. So there are 2 values, 2 consecutive values, so that with high probability the chromatic number takes one of these 2 values with high probability. Yes, so here if you draw such a GMP, you work out the chromatic number, you can predict the chromatic number of the next GMP with high accuracy. So these kind of very sharp upper bounds on the concentration of the chromatic number led Bollobás to ask, well, whether this is always the case, or at least always the case in all interesting examples. So we already know for some strange P, if you let P tend to 1, you do actually need root n values, but how about non-trivial cases? So in particular, he asked, can we show anything for the chromatic number of gm1/2? can we show that that is at least not concentrated on a constant number of values, say 100? Now, if you compare this to the best upper bound by Alon, you can see this is not anywhere close to this upper bound. Yeah, but even showing that it's not concentrated on a constant number of values turned out to be quite hard. And I think the reason it was hard was that we don't really know how to get lower bounds for concentration. So we have these methods. We have concentration inequalities which give us upper bounds on concentration. So for example, the martingale concentration argument by Shamir and Spencer. We don't have a lot coming from the other direction. So so in some cases, for example, you can work out the entire distribution of some random variable, and that implies then a lower bound of concentration. But short of doing that, there isn't a lot. So in this talk, I want to tell you a little bit about how the following result is proved. Okay, so the result is, so whenever you have a sequence of intervals, S and Tn, which contain the chromatic number with high probability, then there are infinitely many values n, so that the intervals are long. How long? So that the intervals have length at least n to the 1/2 minus epsilon, where epsilon is an arbitrary constant. And of course, instead of a constant, you could also put in some function that tends to 0 slowly enough. Okay, so in 2019, I had this result up to n to the 1/4, and recently, together with Oliver Riordan, we've been able to get this up to 1/2, which is nice because this is the same exponent as the upper bound by Alon. So up to this kind of epsilon, or the little one term, which tends to 0 slowly, this result is optimal. So at the end of the talk, I will also talk a little bit about how close to this upper bound we think this can be pushed. Okay, so I have two things I want to do in the rest of the talk. First, I want to talk a bit about the method, how this is proved. And secondly, I want to talk about what we think the correct answer is for the concentration of the chromatic number, because, well, I should warn you right now. So this result only says there are infinitely many values n, so that this lower bound holds. We don't have anything for every n, and we don't actually think this is true for every n. So we think for some n, this is not the correct answer. So this is the second thing I want to talk about, something we call the Zigzag Conjecture, on how we think the chromatic number, the concentration of the chromatic number behaves. Okay, so let's start with the proof method. Okay, so how do we actually get non-concentration? So the proof needs 2 ingredients. The first ingredient that we need is actually a concentration type result. So to prove non-concentration, first we need a weak concentration type result. And we need concentration, well, we don't just need that there is some concentration interval, but we need it to be explicit. So we need some well-behaved function f of n, so that the chromatic number is close to this function, up to some error term. And we also need a lower bound on the slope of this function. So yeah, we need it to increase with at least some rate 1/alpha. I'm going to say in a minute what alpha is. But right now you don't need to know it yet. So we need it to increase by at least 1/alpha if you increase n, plus some leeway. Okay, so that's the first part. What's the second part? The second part is a coupling result that compares the chromatic number of Gn1/2 and a slightly larger Gn'1/2. And what does it do? So if you let n prime be n plus alpha time r, again the mysterious alpha, then we need to show that the chromatic number of Gn1/2 increases by at most r with some sufficiently high probability. So I've written a quarter here, but it's not important that this is 1/4. It could also be 1/1000, but it has to be some constant. Okay, so these are the two ingredients. What do they do? So first, let's just say what the second ingredient does. The second ingredient says that if we have some intervals that contain the chromatic number, S and Tn, and we increase n by alpha times r, then the difference between the two intervals is at most r. Because with probability, so if we generate g in 1/2, with high probability, the chromatic number is in here. If we generate gn prime 1/2, then with high probability, the chromatic number is in this interval. And also with probability at least 1/4, the chromatic number goes up by at most r. So, and this implies that the difference here between these intervals can be at most r. Okay, so if you increase n by alpha times r, then the interval shifts by at most r. Okay, so how do we put these two ingredients together? So this is best seen in a picture. So the concentration type result says that the chromatic number is close to this function, this explicit function f of n. So up to some error term. And this error term is kind of much larger than the scale on which we are trying to prove non-concentration. So we have some fairly wide blue band that we know the chromatic number is in with high probability. And also the slope here is bigger than 1/alpha. And now suppose we have some intervals, S and Tn, which also contain the chromatic number with high probability. Then the coupling result tells us that if we go to the right by alpha times r, we go up by at most r. So the slope kind of the red lines between the intervals is at most 1/alpha. Okay, and now maybe you can see now what happens if we assume all the intervals were very short. If they are all very short, then eventually this leads to a contradiction. Because if we start with some interval, we go to the right, it increases by at most with a slope less than 1/alpha. Then within the interval, we go up by only very little. Then we go to the right again with some not too steep slope and so on. Then eventually, if we don't go up enough within the intervals, we will get some interval like this one, which lies outside the blue band. And the chromatic number with high probability is within this blue band, but also with high probability, it's in this interval, and that's the contradiction. So I hope that's clear how you get the contradiction from this. So this means that whenever we start with some n, somewhere nearby, we have to have at least one long interval. And if you plug in what all the numbers mean, you get an interval of length, well, alpha delta r, where delta was this leeway here, and r is the r we put in here. So in particular, we want kind of to get a good non-concentration result, we want the r in this coupling to be as large as possible. Okay, anyway, so this is kind of the structure of the method. Now, how do we apply it in our particular case? So I should finally tell you what alpha is. So I've named this function alpha kind of suggestively because it will be the independence number of the graph. So the independence number is just the size of the largest vertex set without any edges between them. Actually in G1/2, the independence number is something very easy because, well, it's been known for a long time, since the 70s, that the independence number of G1/2 is essentially given by a deterministic function, which I'm also going to call alpha. So everything is called alpha, but that's fine because it's basically deterministic in this case. So there's a function alpha of n, which I'm not writing out, but it's of size log n. And we know that, at least for most n, the independence number of G1/2 is given exactly with a probability by this function alpha of n. So you use the first and second moment method to prove this. Now, why do we care about this? Why would you try to use this function to prove non-concentration? So what does it have to do with colorings? I told you that the lower bound in the Bollobás result is easy, and that's because the lower bound that we have for the chromatic number is given by a very general lower bound that we have for the chromatic number of any graph. So in any graph, the chromatic number is at least n over the independence number. And that's because if you look at a coloring, then every color class, so all the vertices of one particular color, they form an independent set by definition, because, well, if you look at two vertices that have the same color, well, they, by definition, they can't have an edge between them. So all the vertices of the same color form an independent set. So every color class has size at most alpha of G. Okay, and if you have n vertices, the chromatic number is at least n over the independence number. Okay, so that's easy. And that automatically implies a lower bound for the chromatic number of G and 1/2. And in fact, this lower bound is very close to the truth. So in fact, in G and 1/2, we can show that the chromatic number is given by n over independence numbers minus some constant, and the constant is something like 3 or 4. It varies with n slightly. Okay, so this means that we can color G and 1/2 so that the average color class is only a constant below the maximum any color class might possibly have. So we're able to color G and 1/2 with, well, independence number -3, independence number -4 sets on average. And this kind of suggests that, well, an optimal coloring of G and 1/2 should contain kind of most of the very, very large independent sets as color classes. So if you build up your coloring, the first thing you might want to do is, well, let's take all the maximum independent sets, make them their own color classes, and then continue like that. Now I'm oversimplifying, because this is actually not what we think that happens. So we think you do take in all the alpha sets, but then with the alpha -1 sets, you don't actually take in as much as you can. But yeah, so for the alpha sets, we think this is actually true. And I hope that at the end of the talk, I can talk a little bit about what we think the optimal coloring looks like. But yeah, so the intuition is with the maximum independent sets, you really want to take as many of them as you can into your coloring. And that kind of suggests that the chromatic number should vary at least as much as the number of available sets of size alpha. So I'm calling this X alpha, the number of independent sets of size alpha. And we actually know very much about this random variable X alpha. We know how much that varies. We can actually prove using the Stein's method that this is roughly Poisson distributed. And so it varies by plus minus root of its expectation, as a Poisson random variable does. So what's the expectation? So the expectation depends on n. It's given by n to the, well, some function rho, and the function rho is between 0 and 1. And actually, depending on n, sometimes it's close to 0, and sometimes it's close to n, close to 1. Okay, so there are, and in particular, there are some n so that this rho is close to 1, and so root of mu in that case is close to n. And so if we pick such an n, then the number of available alpha sets varies by almost root n, and that then suggests that the same should be true for the chromatic number. And those will turn out to be the n where we apply the method and get this non-concentration result. Okay, so this is alpha. Now, how do we get the two ingredients that we need? Now, luckily, the first ingredient is really easy. So the first ingredient is a concentration type result, an explicit concentration type result, where we have to show that we have an estimate for the chromatic number, and it increases at a rate which is bigger than 1 over alpha. And we already have this. So this is the result from the second slide of the talk. So we have the this estimate for the chromatic number, which holds up to this error term. And if you take the derivative of this estimate, it's sufficiently larger than 1 over alpha by, well, this much leeway, unless the expected number of alpha sets gets very, very close to n. So it doesn't get us all the way up to root n, but it gets us, or up to n, but it gets us kind of fairly close. And it's actually quite lucky that this result exists, because what we had previously, so the best bounds that previously existed, they didn't actually give anything. So this, I didn't prove this result in order to then apply it to non-concentration, but it's lucky that this exists because it's kind of exactly what you need, exactly the accuracy that you need to prove this non-concentration result. Okay, so that's the first part. How about the second part? So this is the harder bit. So how do you prove the coupling result? So we need that as we increase n by alpha times r, where r is something, well, as large as possible, we need the chromatic number of gn1/2 to increase by at most r with some decent probability. Okay, so how do we do the coupling? Now, well, actually, it's easy how to do the coupling. The hard part is to show that it works. So we construct it by just doing kind of the most obvious thing. So you can see that the difference between n prime and n is alpha times r. So it would be very nice if we could kind of embed a gn1/2 into a gn prime 1/2, so that the difference is just kind of, we can split it up into r independent sets of size alpha. Because then also automatically the chromatic number of the outer random graph is at most the chromatic number of the inner random graph plus r. Because if we start with a coloring of this random graph, and you give each of these sets their own color, then that gives you a coloring of the whole random graph. Okay, so this would be nice to have. How do we get it? Well, we get it by just planting these R alpha sets at random. So we just kind of pick R vertex sets of size alpha and make them independent sets, and then include every other edge independently with probability 1/2. Okay, so what have we done? Now the inner random graph is just a normal gn1/2, so that's fine. That does what it's supposed to do. Yeah, it's also clear that in this construction, the outer random graph has chromatic number of the inner, at most the chromatic number of the inner random graph plus r, because as I said, you can give each of these sets their own color. Now the trouble is the outer random graph is not a gn prime 1/2, because we've disturbed the distribution by throwing in these extra alpha sets. So what's needed now is to show that if r is not too big, so if we haven't put in too many of these independent sets, then the outer random graph is still sufficiently similar to a gn prime 1/2. Okay, how do we do this? The key lemma for this is, well, it's actually much easier to study the effect of just planting one independent set at random. So let's call this the planted model. So the planted model is a gn1/2 where we plant one independent set of size alpha at random and include everything else independently with probability 1/2. Then the key lemma is that, well, we can actually work out exactly how much that changes the distribution of gn1/2. So the total variation distance between this model and the normal gn1/2 is given by something of order 1/√mu, where mu is the expected number of alpha sets. Now, if you don't know what the total variation distance is, I will define it on the next slide, but this means that you can couple this planted model and the normal gn1/2 so that they agree with probability 1 minus total variation distance. Okay, so let's see how the key lemma is proved. Now, as I said here, these models are so simple that you can actually work out the total variation distance exactly. So the total variation distance in this case, because everything is discrete, you can write it down like this. It's 1/2 times, well, the sum of all possible values these random variables can take. Now, random variable, by that I just now mean the random graph. So we have the sum over all possible graphs on n vertices. And we subtract the probability that the first model comes out as exactly this given graph and the probability that g in 1/2 comes out as exactly this given graph. And you can write these things down exactly. So let's start here. This probability is just given by 1/2 to the n choose 2. So every edge has to come out as present or not present in the right way. And well, for this model, if you have a given graph G, the first thing that has to happen is that your planted set of size alpha has to be one of the independent sets that are present in G. So you have x alpha of G of them. So this counts the number of independent sets of size alpha in G. And this is the probability that you come out, that you pick your chosen set of size alpha. And then all the remaining edges, of which there are n choose 2 minus alpha choose 2, have to come out exactly correctly as they are in G. And that's the probability that the planted model comes out as exactly G. Okay, and now we just need to rearrange terms nicely. So we pull out 1/2 to the n choose 2, and then what we're left with here is, in the denominator, we actually have the expected number of alpha sets. And here we have the number of alpha sets in G minus, again, the expected number of alpha sets. And now the nice thing is here you have a sum over all possible graphs on n vertices, and here you have the weight that these graphs have under G in 1/2. So this, so this is exactly the expectation of x alpha minus mu, absolute value divided by mu. And now we know that x alpha is Poisson, so it varies by something of order root mu about its expectation. So this is of order root mu, and dividing it by mu gives something of order 1/root mu. Although you don't need the Poisson distribution for this, you just need an upper bound on the variance of x alpha, which you can also get easily. Okay, so this is how you prove this key lemma. And now hopefully it becomes plausible that if we repeat this less than root mu times, and each time the total variation distance is of order 1/root mu, then after at most root mu steps, the total variation distance between the normal G n prime 1/2 and this G prime where we've planted our independent sets of size alpha is still little o1, because little o root mu times we add up this term here. Okay. So what this means is that in this model, we can couple this big graph where we've planted our independent sets of size alpha with the normal G and prime 1/2, so that they agree with probability 1 minus little o1. And so overall, what we've constructed is a coupling of this normal Gn 1/2 and a Gn prime 1/2, so that the chromatic number increases by at most r, where n prime is n plus alpha r. And yeah, so this is what we wanted. So this is how you get this coupling part of the construction. Okay, so this is all I wanted to say about the proof. Now, for the second thing I wanted to talk about, what do we actually think the true concentration behavior of the chromatic number is? So if you recall, x alpha, the number of independent sets of size alpha, is some Poisson random variable, roughly. And sometimes mu, the expected number of those sets, is close to n. But sometimes it's actually closer to 1. So if you plot the exponent, it kind of looks like this. So you increase, you start with very few alpha sets, then you increase n, and the expected number of alpha sets also increases. And then at some point, alpha plus 1 sets start appearing. So then kind of the independence number jumps up by 1. So this is why this is discontinuous. Here, the independence number changes. And so, yeah, this exponent kind of drops down to something close to 0 again and increases again to 1. Yeah, so the kind of the variation in the number of alpha sets then increases from n to the 0 to n to the 1/2, and then again n to the 0, n to the 1/2, and so on. And so the first part of the conjecture is that basically the same is true for the concentration of the chromatic number. So the first part of the conjecture is that the chromatic number should not be concentrated on fewer than about root of this many values. And we divide here by a log n. This is because basically the benefit per extra alpha set that you get, you can kind of calculate this, that every alpha set saves you about 1/log n chromatic number colors. Yeah, if you have an extra alpha set, it saves you overall roughly 1/log n colors. Okay. And actually, if you kind of go through our proof, this is actually what we show. So we show that for every n, there's an n star nearby, so that root of this variation in the number of alpha sets over log n is a lower bound for the interval length. Now, is this all, or are there other sources that introduce non-concentration into the chromatic number? So we have this conjectured lower bound coming from the alpha sets. Now, another kind of obvious candidate would be the number of edges, because we have order n squared edges, so that varies by something of order n. So this kind of seems like it might make a big difference to the number of colors that we need. But this actually turns out not to be important. So there's a coupling argument that shows that you can actually couple the GMP with the corresponding GNM, so that their chromatic numbers only differ by about something of order log n. So this doesn't seem to introduce much variation. I don't think it actually introduces any variation, but it varies by at most log n. So actually, Alex Scott came up with this argument, even though the last time I gave this talk, he had forgotten about that. Now, a similar thing to the alpha sets also happens with the alpha minus 1 sets. So you can kind of work out that the number of alpha minus 1 sets is also roughly Poisson distributed, with mean n to the 1 plus rho. You remember n to the rho is the expected number of alpha sets. So you have n to the 1 plus rho alpha minus 1 sets. And well, if you condition on the number of alpha minus 1 sets and kind of work out how many colors you're likely to need, at least so that the expected number of colorings comes out as at least 1. Well, if you do this calculation, you can work out that if the number of alpha minus 1 sets decreases by some typical amount, then you need about this many more colors to kind of make up for that in the expected number of colorings. And so the second part of the conjecture is that this is actually also a lower bound for the chromatic number, for the variation of the chromatic number. Now, okay, so can we maybe continue like this? Can we now get variation from the alpha minus 2 sets, alpha minus 3 sets, and so on? This appears so not to be the case. So I'm currently writing up a result together with Kostas Panagiotou, where we look at the alpha minus 2 bounded chromatic number. So this is like the normal chromatic number, except we've banned the alpha and alpha minus 1 sets. And this actually, kind of surprisingly, appears to be very narrowly concentrated on at most 2 consecutive values. So it appears to be that this actually, so the smaller sets don't actually introduce any variation. So here's finally the conjecture, which we call the Zigzag Conjecture. So this arose from the work of several people on this topic in recent years. So there's Bollobás, Rob Morris, Kostas Panagiotou, Oliver, and Paul Smith. So here's the lower bound coming from the alpha sets, which increases kind of from n to the 0 to n to the 1/2. So this is, I'm just plotting the exponent here in n. This is the lower bound coming from the alpha -1 sets. It kind of goes down the other way. And the conjecture is now that the true value kind of is the maximum of these 2 bounds. So that the concentration of the chromatic number varies between n to the 1/4 and n to the 1/2. And if you plot it on a log scale like this, it actually goes up and down in straight lines like this. Okay, we also have a number of finer conjectures. So in particular, we think we can predict a Gaussian limiting distribution. We also think we have an idea of what happens at the minimum and maximum. So we think in the best case here, these are the kind of the correct log factors. So this is just where these 2 lines intersect. Now the more interesting case is up here. So we think at the top, the concentration is root n log n over log n cubed, which kind of looks a bit weird, and there's no quick way of saying why we think this is the answer of all things. So this is because, well, I've already told you that here, an alpha set, if you get an extra alpha set, it saves you 1 over log n colors. So this is true almost all the time. But as you get close to this kind of top point, an alpha set kind of gives you less benefit. So the number of the variation in the number of alpha set increases as you get close to this point, but the benefit per alpha set decreases. So you have a product of an increasing and a decreasing function, and it's maximized. So if you work this out, and it takes actually a lot of work to work this out properly, but if you do, you find that the maximum of this product is this. It's root n log n over log n cubed, and we think it's reached at where you have n over log n squared alpha sets in expectation. Now, how close to this can we actually get? At the moment, we can't actually do anything better than n to the 1/2 minus some unspecified term that tends to 0. And the bottleneck is the error term in the explicit estimate for the chromatic number, so in the first ingredient. But also in this paper, which I'm writing up together with Kostas Panagiotou, we have a sharper explicit estimate for the chromatic number. And assuming this estimate, we think the method actually gets us all the way up to what we think is the optimal non-concentration result. So yeah, we think this is optimal, and assuming this second moment thing we're currently writing up, the non-concentration method can actually get us up to the constant, what we think is the optimal result for infinitely many n. Okay, I'll stop with some open questions. So the most obvious one is proof that the zigzag conjecture holds. Does the correct concentration interval length actually zigzag between n to the 1/4 and n to the 1/2 along this line? Short of that, so a problem with the method is, kind of an inherent problem, is that it only ever shows that close to every n there's another n star, so that non-concentration holds, but it gives you nothing whatsoever on any particular n. So it would be very nice to get anything which holds for every n. Now, as I said, we think we can push the method all the way to what we think is the optimal result, but of course we can't prove this is optimal. So it would be nice to close the gap between this and Alon's upper bound. So these two only differ by log squared now, but they're still different. And finally, all of this was about d(n)1/2. Most of what I've said also generalizes to other constant p. So in particular, we can show that for every constant p, there are these long intervals of length n to the 1/2. Now coming up from n to the -1/2, we know here we have very narrow concentration. So it would be interesting to see where this changes. So how, if we go down from p constant, how long can we prove non-concentration? Or coming up from n to the -1/2, can we push this very narrow concentration for a little bit longer? And that's the end of the talk.
So thank you very much for excellent talk. So please unmute yourselves and join me. And we will hand over to Moscow and continue in about 10 to 15 minutes.